Many thanks to Pinaki and Arnab for organizing this meeting and bringing everyone to IMSC. Okay, I'll talk today about aggregation. This work is done with Subhashri, who just graduated, and based on this paper. So, aggregation of particles that are transported is the dominant physical process in many physical systems. So I'll give you a few examples that I'll just show to show that aggregation is ubiquitous. So consider a river network where the river starts in the mountains and they form tributaries which join to form bigger rivers and finally reach the sea. If I look upon this as time axis and this as x-axis, then these things joining together is like aggregation. Two random walkers come and aggregate together. Another example is Saturn rings, where you have these ice and dust particles moving around. They collide, shatter, and sometimes they aggregate and maintain some non-equilibrium steady state. Both of these are at the scale of kilometers. Then at the micrometer scale, you have an example of cancer cells when put into a medium, aggregating together to form big clusters, increasing their virulence, for example. And this one is an example from dust particles forming soot. And finally, a couple other examples from other very different systems. One is from ductile fracture, where you form voids, and these voids coalesce to form bigger voids till the system fails. And another example from polymers. Polymer aggregation is common in Alzheimer, mad cow disease, and so on, and is crucial to avoid. So I showed some slides to show that aggregation is ubiquitous. Now there are two features in all these processes. One is the transport to big clusters together, and the other one is when they come to contact, they aggregate. So when you model, you have two options. Either you model transport and aggregation separately, or you combine them into an effective collision kernel. Okay, you just say that the rate of collision is something and they collide and become a bigger particle. Now, I will take this, in this talk, I will take this particular approach and I'll tell you what I mean by that. So let me first define a model that has been studied for many years. I'll call it cluster-cluster aggregation. So at some point of time, let there be a collection of particles, and each particle is labeled by some mass m1, m2. In general, a mass which is integer mass. And then the system evolves in time by a simple, just one dynamical process. Two particles coagulate at some rate to form a bigger particle. So two particles become one particle, but mass is conserved. And the rate of collision, I'll call as collision kernel. In general, it could be mass dependent. Okay? It depends on both the masses colliding. And you start with, let's say, capital M particles of mass 1 or mass m0, but we measure everything in terms of that mass, so we can set it to 1. And in one collision, mass is conserved, the number decreases by 1. Okay, this is the model I'll focus on. Now, so let me give you an example of what is a collision kernel. So if I look at ballistic particles, particles that move in a straight line and they collide to form a bigger particle, then if we look at the rate of collision, you can imagine it is proportional to the relative velocity and is proportional to the radius of cross-section, area of cross-section, which is r1 plus r2, the radius of the particle to the power d minus 1. Now in kinetic theory, we normally write this difference as square root of the RMS velocity. And if you assume spherical particles, then this becomes mass to the power 1 by d. And then you can convert the velocity to mass using momentum conservation to get the collision kernel which you use in kinetic theory. Okay. So likewise, depending on the system you study, you can create an appropriate collision kernel. Now, this particular problem of aggregation has been studied for a long time, pioneered by Smoluchowski in 1917. And he proposed this equation, the coagulation equation, which is only an enumeration equation. Okay, so let me just describe. So you look at the number of particles of mass m at time t. So there's a distribution, and this distribution is evolving stochastically. But the idea is that to write a mean field equation for the mean mass distribution, so you ask, how does it change with time? So if I have a particular at one instant, it can change due to two terms. One is when two particles collide, which are different from mass m, and they combine to form a mass m. So you write this as density of particles of mass m1 of mass m2 colliding to form a mass m with this corresponding rate. And then there's a loss term. You had a mass m, it collided with another mass m1, and that to form some other mass, which I don't care. And that loss term comes with the density of particles of mass m and the density of particles of mass m1. Okay, so this is you can write this down by inspection. Okay, and this, since each collision conserves mass, this equation also conserves mass, but sometimes it doesn't. Yeah, so this particular equation is a mean field equation. It ignores all fluctuations and just looks at the average mass distribution. Now, this equation is solvable only for solvable in the sense of exact solution for mass distribution, only for three kernels, and they come all the time. So let me just list them down. One is the constant kernel, in which two particles, when they collide, the collision rate is independent of the masses. Okay? And then there is another one which is called the sum kernel, where the collision kernel is the sum of the masses, and a product kernel where it's the product of the masses. Okay? And here, the typical mass, so as time goes on, larger and larger masses are created. The typical mass happens to go as time, as t. Here exponential in t, and here there's something funny happens. So I will just tell what's this funny thing that happens for this product kernel. So for the product kernel, when you solve for the mass distribution, you get some answer. Now the precise form is not important. But if I look at the second moment diverges at time t equal to 1. Okay, and this transition in the literature is known as the gelation transition. So what happens beyond this transition? You have to find the solution. The Smoltowski equation is the solution for infinite mass equation. So you have to find a solution for finite mass, and this solution is a complicated solution depending on something called Mallows-Riordan polynomials. And so if you do a simulation, you take these particles in a box, make them collide in this particular rule. You measure the mass distributions various times. So this is the mass distribution at time 0.5, at time t equal to 1, you get a power law. And at time t greater than 1, you get a condensate that forms. Okay? This condensate is called the gel. It contains a finite fraction of the mass. And the solid line is this particular equation that I have written. So this was a brief summary of what is known for the Smoltowski equation analytically. There are a lot of numerical techniques for solving the equations depending on the kernel you study, but that I'm not focusing on in this talk. So so now what I am going to focus on in this talk is what are the probabilities of rare events. Okay? So to remind you, the Smoltowski equation does not address any fluctuation beyond the mean value. So for example, if I were to look at just the number of particles, not the mass distribution, and I solve the Smoltowski equation, I get this black line. It decreases with time. But I could ask, what's the probability of this red line, or which is away from the typical? Okay, this I'll call as rare events. So if I fix a time, I could ask at this time, instead of the typical value, I get the number of particles to be much larger or much smaller. Likewise, if I fix a particular density, at what fraction at time does it reach that particular number of particles? Now, if I want to define some quantity that captures this, I'd like to ask what is the probability of starting with m particles, finding n particles at time t. So if I can answer this question, then I describe the stochastic, the model I described completely. Okay. As now, usually in the literature, when you want to study events away from the typical, that is described by something called a large deviation function. So I sort of assume that this audience is familiar with large deviation function, at least they heard the word before. So in the remainder of the talk, what I will do is I will tell you how to calculate this probability of having n particles at time t starting with capital M particles, and present an exact result for the 3 kernels for which the small source equation was solvable. And so let me summarize the results of the talk. The remaining talk will be a bit technical, but I will summarize what we find here. So what we find is, if I look at this probability, it has the large deviation form e to the power minus the total mass in the system in the function of the fraction of particles remaining and time scaled by m. Okay. Which means that I can identify m as a rate and f as a large deviation function. Now, this particular form can be shown for any kernel. Then the exact, but the form of phi, what is the precise form of phi, can be found only for constant sum and product kernels. Okay? And in addition, you can ask, if I have a rare event, given a rare event, what is the trajectory that contributes to that? It is possible to calculate the most probable trajectory for these kernels also, for any given rare event. And finally, I'll also argue that the large deviation function has a phase transition in the sense it has a singularity at some values of tau and phi. Okay, so let me outline how does one go about solving such a problem. So so at any instant of time, if I ask what is the configuration, so I can ask how many particles are there of mass 1, mass 2, mass 3 and mass n. If this vector tells you the configuration of the system. Then it's a Markov process, so its evolution is controlled by the master equation, which has this funny form. The precise form is not important, but the probability distribution evolves by the master equation. Okay. Now, the idea is to write this master equation in a form which is like calculating in terms of an effective action. And there is some set of steps, one procedure for deriving this action, which the one I'll follow is called the Doi-Pelitier-Zeldovich procedure. What it does is it introduces annihilation and creation operators to write the master equation as a Schrodinger equation, like a Schrodinger equation, and then convert that into deriving effective action for the problem. So I'll just give one slide description of how this is done. So the key thing is to introduce a wave function, something like a wave function, which is given a state and its probability sum over this particular quantity. If I were to define this wave function, then the master equation after some manipulation can be written like a Schrodinger equation, okay, where you have to introduce in terms of the annihilation and creation operators. So for example, for the problem for aggregation, the Hamiltonian looks like this. So the only difference is that this Hamiltonian is not Hermitian. Otherwise, it has the form of a Schrodinger equation and with a solution which has this form. Now, the relevant quantity we were interested in is what's the probability at the final time of a certain configuration. That happens to be some particular inner product with this wave function. Okay. And you get some complicated expression of this kind. Finally, you introduce coherent states to convert and to derive an effective. These are all well-known procedures, but once you do this, then you find that the probability that we want of finding n particles at time t can be written in terms of a action S, okay, provided you scale your time and your n in this manner. That is what I said, that if you in the scaling form, there's a large deviation form once you scale like that, okay. It looks a bit messy, but the point is there's an action which has a certain form in which the boundary initial condition and the final condition comes in. So the point is the action depends on the dynamical process as well as the initial and final condition. That is important because these final and initial condition finally contribute to the large deviation function quite a bit. Now, if I were to stare at this equation, it has the form e to the power minus m times some action. And in the limit m going to infinity, all you have to do is minimize the action to get the leading form for this probability. Okay.
M log n, sorry. N large and m large keep the ratio fixed, but you also have this t small m large keeping the polarity.
Yes.
So in some sense, a short time result, or
no, even in the Smoltowski equation, if you don't do the scaling, you don't get a reasonable, sensible answer. Even in the when you take m going to infinity, you have to scale. That time is already scaled in that fashion.
so
For example, in if you look at the product kernel, in the gelation occurs at 1 by m. So only when you scale m with t, you get a finite gelation time.
is there any simpler to see why this longer m scaling comes? What's the time scale?
Why? I don't know, but I can think and tell later. Now, even for the sum kernel, you have to scale. So now there's an action we want to minimize, and then the minimization is given by the usual Euler-Lagrange equation. Okay. But with some funny boundary conditions. So there are two variables z and z tilde, and they obey boundary conditions of this kind. So the Euler-Lagrange equations have to be solved for z and z tilde with these boundary conditions. Now it turns out that with some effort you can solve for these three constants, sum and product kernel. So I'll just tell you the results for them and show that with simulation that they are the right answer. So the first claim is that so if I go back to this equation, I minimize this. Then the claim is that if I take the logarithm of this and with m, there's a finite limit phi, which is a rate function. This is true for arbitrary kernels. Okay. Now, for the constant kernel, you can find the solution. The solution depends on, one more point I have to tell. So once you have an Euler-Lagrange equation, the Euler-Lagrange equation conserves the Hamiltonian. So if I start with a certain energy, that energy is conserved. So there is a parameter E, which is you can control. And that E is what comes in this equation. And the form of this equation is complicated. There's no particular sense in trying to understand what this form is. But the large deviation function, when plotted for fixed time and changing phi, looks this solid line. Now, the E equal to 0 corresponds to this bottom, which is the typical answer, which is so the Smoltowski equation corresponds to this particular point. Okay, and the data is from a simulation which is directed towards determining low probabilities in such problems. Okay, and they match quite well. In addition, you can ask, given a particular phi and a rare event, what is the trajectory? And that trajectory also we can compute. What is the mean mass, time, mean number of particles as a function of time for different tau typical. So I can look at tau typical, I can look at times which are 5 times tau typical or tau typical by 5, and you can compute the trajectory that contributes to the large deviation function.
Sorry, Rajesh, these are interesting hints. Like it's in your, so
Yeah, E comes in, it is determined in terms of the boundary conditions, but in this particular case, it's complicated to calculate that. Similarly, for the sum kernel, you have a simpler form for the large deviation function. This is a large deviation function. This point corresponds to the Smoltowski answer. And you can see that the answer matches quite well. Uh, uh, and likewise, you can compute the trajectories for any, given any rare event, you can compute the trajectory for that. So these two are, so they're just some functions and they're not so interesting. So finally, in the product kernel, we could calculate the large deviation function in terms of the final, the phi, the tau. But there's a complicated expression in terms of something called Mallows-Riordan polynomials. Okay? And so when we evaluate this, see, for example, if I look at tau equal to 3, this is much beyond the gelling time, but the large deviation function one can calculate even for them that time, and it matches quite well with the simulation. Ignore these parts here; these are sort of finite size effects from the simulation. Okay. The interesting part is, so if you take the large deviation function and take a second derivative with respect to phi, it happens to have a singular behavior. So I'm plotting the second derivative with respect to phi, and there's a jump at a certain phi. So I'm fixing tau, I'm plotting as a function of phi, and it has a jump singularity. Okay, and these are for different times, fixed times, 3, 2.5, 2, and 1. And what happens, so there must be some difference of behavior in the most probable trajectories on the right and the left. And on the right, we find that the most probable trajectories have no gel, and on the left, you find that the most probable trajectories have a gel. So that's a numerical finding. So that causes a singularity in the large deviation. So that so I have quite a bit of time. So let me now, so I can go slowly here. So aggregation is an old problem. It's an infinite species problem. If I consider each mass as different, it's an infinite species problem. And so we are able to compute LDF for 3 standard kernels, and we could explicitly show it is singular for the product kernel and expect it to be singular for all gelling kernels. What I didn't say is that we can compute many more things like mass distribution along a trajectory. So why is this important? The importance comes from the fact that aggregation has both experimental and theoretical interest for a long time. But this angle that going beyond the mean or the fluctuations about the mean has not been possible up to now. And therefore, this opens up a new paradigm in aggregation. Right? So that is the main contribution. Now, so let me spend some time on some of the directions we are looking at. So one direction is we are able to solve only for 3 kernels. So you can ask, can you have Monte Carlo algorithms which look at rare events in an efficient manner? So for that you have to do what are called biased Monte Carlo simulations. But for aggregation, it's a bit complicated. So we have come up with some complicated algorithm for biasing the simulation, which we published in this journal. But now with the calculations in hand, one thing we realized is that for reasonable kernels, even though if you look at the optimal path, the sequence of collisions don't seem to change. So if I look at, for example, if I look at constant kernel, as at the 5th collision, irrespective of what the final time is, the mass distribution has to be the same because the 5th collision. So if I use this, assume that the mass distribution as a function of collision does not change much from the typical, then it is possible to have simulations in the Laplace space, which seems to be an improvement in both speed and efficiency. So I think this seems possible. This is one direction we are trying. Then one thing I could not explain because of the complicated nature of the derivation. For the product kernel, when we try different derivations of the action, we get different large deviation functions. That part was hidden in the thing, and we had to look at the correctness based on which equation gave the right uh, typical answer. So then there is some confusion there. And so one question we are interested in is, can one find an alternate exact solution of the product kernel that does not rely on this procedure? So we have been trying something based on some replica breaking, symmetry breaking calculation. It seems to work, but not at all points. So that is one direction that is good. And other questions which we are interested in trying. So I was looking at P of m comma n comma t, where n scales with mass to find the large deviation function. But you can ask when this n does not scale with mass. For example, what's the probability of having all things clustering at time t? Now the scaling will be different. The calculation is similar, but can we calculate this and make some pattern out of this one? Okay. The other one is, if I look at the most probable trajectory and ask what is the probability of fluctuations about them, this also seems calculable within this procedure. And so another interesting problem of aggregation is when there is aggregation, but there is also input of particles, so it is a steady state. So can the formalism be generalized to compute them, both the input as well as the space involved? And other obvious generalization is, instead of binary collisions, if we look at quinary collisions. This we wrote a recent paper on that. And one more thing we are very much interested in is, so if I look at generic kernels, if I look at a kernel, I look at a kernel which is characterized by two exponents mu and nu. So for example, for constant kernel mu is 0, nu is 0. Some kernel mu is 0, nu is 1. And for product kernel nu is 1, mu is 1. So we have a phase diagram like this. This is from the analysis of the Small-Chor's equation. So it says that when mu plus nu is less than 1, there is no dilation. In this particular area, bounded by the sum and the product kernel, there is gelation, but at finite tau. Then there is, in this region and this region, there is, the moment you start the simulation, there is a gelation, instantaneous gelation. And here, I don't know the exact meaning of what this says. It says no solution, but it also is, I think all the particles become one. I don't know. So what we were trying to do was to ask, if I work with finite masses, not infinite masses, can we make sense of these regions in terms of large deviation first? So for that, you have to write some Monte Carlo codes which are go beyond the regular. It has to be more efficient with some algorithms, so which we have succeeded in doing. So we are hoping to investigate not just these 3 points, but the remaining points numerically. That is the point, and I'll stop.
In one of the slide, you talked about finite size effect. So can't we get rid of the finite size effect by increasing the boundary?
Which? Yeah. So this one I said. Yeah. So I didn't describe the algorithm that we use. So it's a bit time consuming. And so for example, on the left, if I keep phi fixed and change time, those simulations you can see are very clean. But when I fix tau and change phi, there's a problem. So the simulation, how it works is, you take a trajectory from time 0 to t, and there's a trajectory that follows. Fix the 2 times, and then you make perturbations in this trajectory. And then sometimes when you make a perturbation, then for it to equilibrate further, it takes a lot of time. So which is the difficulty here. So one could improve, but one has to. So the alternate algorithms we are trying seems to be overcoming these problems.
So my question is with the toyability formalism. So if I understand it correctly, you're going from like a discrete model to a continuous model and take some kind of limit, right?
No, mass is still discrete in the action. It is integer. If I were doing a lattice model for with space involved, that there I can take the continuous limit in the action, but I need not take there also, but I should take.
So is phi not like a field here, or is that still
The z tildes are those are continuous. Z tildes are so for each mass there is a z and z tilde, and the z tilde themselves are continuous, but the m itself is discrete.
So also when you get the action, like is it always possible to see what is the corresponding stochastic differential equation to that?
No, if you want to find the corresponding stochastic differential equation, some of the actions when you get, you can do the Hubbard-Stackles transformation and get back the stochastic differential equation. But some actions you cannot. You cannot find. There's no obvious way. But depending on the reaction differential system you're looking at, you might or might not get.
I have experience to analyze the cluster-cluster aggregation based on the Doping comparison, and it looks your theory is only applicable to the Mie field, even if dimensional.
No, you can include.
But that is so. If you are interested in the finite dimension, including the fluctuation effect, so it must play the dynamics must play the role. For example, original Doping formalism is based on the diffusion cluster aggregation. So if you are interested in the ballistic aggregation, it should be different from the diffusion. I don't find any dynamics in the process. This is one question. Another one is that I found limitation of the such method because that method cannot describe the shape of the clusters. So the original Mie field description assumed that the cluster is a spherical, and including the effect is a cluster aggregation kernel is involved. Describe effectively the effect of the shape or something dynamics, but this is not the case of the Yale description. Is it possible to describe this?
So the first question. So there are two things contributing to fluctuations. One is just the fact that from stochasticity of the reactions, and one is coming from the transport, like diffusion. Now, so that's why I said in the first process, I'll take the approach in this talk where the kernel incorporates a transport into the in this. So
It's in chemical reaction.
yeah, these are like in chemical reactions. So the point is that it has not been possible to compute even this with ignoring diffusion. It has not been possible to calculate. Now you can ask, if I include diffusion, what will happen in the, so then the action you can write for that. But when you write the Euler-Lagrange equation, it becomes partial differential equations. So then it becomes difficult to compute. But then, the way people compute in other, I don't know, in symmetric exclusion process and all, I realize that if you look at the Laplace transform of the probabilities, and then you do an expansion in that, you may be able to compute them order by order. It is possible. That's I do not know. But the point is, you can write the same Euler-Lagrange equations with diffusion put in. Solvability is a problem. Now the second comment about clusters becoming, I agree. This is the dilute limit of that, and if you include space, you have to do a simulation. You cannot do anything else. No, not space. If you include complicated geometry for the clusters, you have to do a simulation, and the low dilute limit is described. The scaling laws are described by these problems, but not the time when it becomes too big.